Hello, this is the Mr. Maths channel. Today we're going to be learning about roots of polynomials, which is the second topic following on from complex numbers. As well as using the information that we learned in the previous topic, we're going to be applying that to the solutions of polynomials and seeing what the coefficients and the roots, or rather the solutions, have to do with each other and what kind of relationships they form. Now suppose we have a very simple polynomial. We have a quadratic, which you would have encountered in Key Stage 3, Key Stage 4, and also in your A-levels. So let's take a very simple quadratic, x squared minus 2x plus 1, which equals 0. Now this quadratic will have solutions x equals 1, as you can very clearly see. So just by factorizing it, what we get is x minus 1 times x minus 1, because these two values add up to minus 2 and multiply to 1, which equals 0. So x will equal 1. This is just a single root, or rather a repeated root for this quadratic. Now what we will do is we can say that this quadratic has two roots and they're just repeated. So what we can actually say is that there is a root which we will say is alpha. Alpha is one root which will be equal to 1, and there's going to be beta, another root which will also equal 1. It just so happens to be that alpha equals beta, but there are two roots. Now let's do some elementary operations and see what these two kind of result in. So the first thing that comes to mind is adding them together. So let's do alpha, beta, and it equals, in this case it will equal 2. Now if we were to multiply them now, so we'll just have alpha times beta, then that will just equal 1 times 1, which is 1. Now it's probably not immediately obvious as to what this might entail, what these actually equal in relation to the original question. These might just look like random numbers, but I'll make this a little bit more obvious by kind of making this quadratic into a general form of sorts. So we're going to have this quadratic, which is in the form ax squared plus bx plus c equals 0. Now if I were to divide everything by a, okay, we get x squared plus b over ax plus c over a equals 0. Now we know that a is just 1 here, so b over a will be just the same as b. Same with c, dividing by a will just also be c, because a in this case is 1. Now what you do realize after looking at this for a little bit is that alpha plus beta, which equals 2, is just the minus of the coefficient of x. So if we know that 2 or minus 2 equals b over a, then what we can deduce from that is that alpha plus beta is equal to minus b over a. This isn't exactly a very strong proof, but it works regardless in terms of the intuitiveness of the problem. So same thing over here, alpha beta, if we were to look at this term over here, this 1, we can see that it correlates to c over a. So alpha beta will be c over a, because c over a equals 1 and alpha beta equals 1. These are called Vieta's theorems, and all of the questions regarding roots of polynomials, from proof to transformations of graphs to arithmetic and geometric progressions, will involve these sorts of principal identities, if you will. Now there are a little bit more complicated examples. Some of them involve higher order polynomials like cubics and in WJC they will go up to quartics. So let's take, for example, 3x squared minus 6x plus, or rather 6x squared plus 18x minus 54 equals 0. Now, if I were to ask 3x cubed, sorry, if I were to ask you what is minus b over a equal to over here, and you will say, well, b over a is 6 over 3, because this is a cubic, right? For a cubic, the general form is ax cubed plus bx squared plus cx plus d equals 0. And now that you realize that b over a would just be minus 6 over 3, which would be minus 2, what we can clearly deduce from this is that if we add up all the roots of this equation, and because this is a cubic, it will have 3 roots. It will have alpha, which is one root, beta, which is another root, and gamma, which is the final root. So because you have to consider 3 solutions, you have to include them in your Vieta's theorems as well. And they don't change them that much, and it's the same principle regardless. So if I were to make it a little bit more obvious, just divide everything by a already. So x cubed plus b over ax squared plus c over ax plus d over a equals 0. We're going to have our first Vieta's theorem, which is going to be alpha plus beta plus gamma, which is the sum of the roots together, will be equal to minus b over a. And then we're going to have the sum of the pairs of the roots, which we're going to add up to c over a. Now, what I mean by the sum of the pairs of the roots is if you were to just consider 2 roots, alpha and beta, the sum of the pairs of the roots will be every unique combination of 2 of those roots together, multiplied and then added. What this results in is that you have alpha and beta, of which you can only make one unique combination and add together, which is just alpha beta. As in beta alpha is the same, so you can't really add that onto itself. With alpha beta gamma, however, there's a different story. To choose 2 options from alpha, beta and gamma, so as to not make any repeats of your multiplications or not to multiply the same thing together, you can first of all use this sort of method and then learn to kind of spot the missing term for yourselves. Now, if you were to kind of make loops around these multiplications, you'll get 3 distinct terms, and as we can see, we've covered every single term on the board over here. So the first term will just be alpha times beta, so alpha beta, and then we add the next term, which is going to be beta times gamma, like this, beta gamma, plus, and then alpha gamma going this way, alpha gamma, which equals c over a. And of course there's the final term, which is going to be d over a, or rather minus d over a, which will equal the sum of the triplets of the roots. Now the case over here is that because there's 3 roots, alpha, beta and gamma, there's only one way to uniquely make a triplet out of these, because there's only 3 of them. Like I said before, there's no other unique way to multiply them together and get a separate kind of number. So it's just going to be alpha times beta times gamma. Notice how the negative sign kind of repeats a pattern where it starts with minus b over a, becomes a plus with c over a, and a minus with d over a. So if I were to ask you what the next term would be, let's say in a quartic, let's say it will be e over a, right? It will have a plus in front of it because the minus sign kind of repeats this sort of pattern, which you need to be aware of. Now, we can apply this even further to a quartic, although you'll really get asked a question to work with these sorts of roots. There's a lot of methods that you can use to solve quartics, for example, which is mainly what you're going to get asked, but it is useful to know. Also, it kind of gives a need to learn new notation, which I will show you. For example, let's say you have a general quartic. You have ax to the power of 4 plus bx cubed plus cx squared plus dx plus e, which equals 0. Now this quartic has 5 terms, which you have to consider. Okay, if you just divide by a, okay, then you have everything down from x cubed, which you have to kind of work out the Vieta's theorems for. So let's try and do that. And then that equals 0. Now, if we were to kind of look at the numbers in front of the x terms, so the number in front of the x cubed term, which is called the coefficient, okay, is b over a. For b over a, or rather minus b over a, it will equal the sum of all the roots together. Because this is a quartic, there will be 4 roots, and we're going to define those roots as alpha, beta, gamma, and delta. So now, as we know, that minus b over a is just all of these roots added together. Essentially, you're just kind of writing it down, adding a plus, and then that's it. C over a is where it gets a little bit tricky, because now you have to consider the number of pairs or unique combinations that you can make out of 4 roots, which is a lot. Again, you can use the method that I showed you before, where you can just have alpha, beta, gamma, delta, and then kind of list the roots over here, and then make these sorts of combinations. And then what you do get out of this is 4 unique combinations. But this is very cumbersome, especially for higher order polynomials. The combinations get huge and it just increases, and there's a very high chance that you'll make a mistake. So what has been introduced to counter that is sum notation. Now this may look a little bit scary if you were to look at it first, but what I will say is that once you get the hang of it, it's really easy. Also, most of the substitutions that you learn later on, which is what we need to learn in this topic, they will involve some sort of sum notation that you can learn and just quickly apply in the exam, and it'll be really easy. Now, minus b over a, I will say, is just all of the single roots added together. So this just means sum, okay? Just one root, okay, summed together with another root, okay, going to all of the roots possible. So this just means sum of the roots, okay. Now c over a, what I will define as, is another sum of the pairs of the roots multiplied together, okay. And then in this sort of fashion, what you can do is you can keep repeating and say, now minus d over a will just be sum of the triplets of the roots. And then, because this is a quartic, e over a in the end will just be alpha, beta, gamma, delta, because there's only one distinct way to multiply 4 roots together. Now let's try and apply this into a question. We're going to have our first question, which is going to be a graph transformations question, which is probably the most common question, I'd say, in these sorts of examples. The other types of questions you can get asked are proofs, and you could also get asked some odd questions, such as find the coefficients of the original equation using the roots, trying to work backwards from your given information in the question. So let's first of all define a function. Don't get scared if I use these sorts of words. Let's just think about this f of x as being like a pseudo y, just being a thing over there that says that there is some expression of x out there which is defined as x cubed minus 8x squared plus 25x minus 26, right? So there's just this expression, okay? And let's say that this expression, okay, this collection of coefficients and terms will just equal 0. Now, what we do know is that because this is a cubic, it will have 3 roots. It will have alpha, beta, and gamma, where f of x equals 0, or the function of x equals 0. Now, what we're tasked to do is find another function, g of x, which we don't know the coefficients of. However, what we do know is that this has to be a cubic, because what it's trying to tell you is, it's trying to tell you to find this expression, okay, when you know that the roots, in terms of the previous question's roots, are 13 over alpha, 13 over beta, and 13 over gamma. Now, what we do know about this sort of expression is that it has 3 roots, then that means this has to be a cubic as well, especially because we're transforming this, okay? You can't transform a polynomial and result in a higher order polynomial. Now, g of x, okay, now that we learned what a general sort of cubic looks like, will just be equal to ax cubed plus bx squared plus cx plus d. And we're trying to find the roots of the equation, or rather we already know the roots of the equation and we're trying to find the coefficients. So when g of x equals 0, the roots of the equation are 13 over alpha, 13 over beta, and 13 over gamma. Now, it may not be immediately obvious what you need to do, but the obvious thing, or rather the thing you should do first, is consider what de Vieta's theorems are. It's always a very nice step to start with, because obviously it will be an independent mark in your exam, but also because it's just kind of like a gateway into solving these questions. Now let's say you have f of x over here, and these sort of roots, those will add up, okay, and they will have minus b over a. Now minus b over a, because a is just 1 over here, we'll just consider minus b. And since b equals minus 8, we'll just say alpha plus beta plus gamma equals 8. Now, we're going to have alpha beta plus beta gamma plus alpha gamma, which equals c over a. And c is just 25. As a is just 1, I reiterate, it's going to be 25. Same thing with the product of the roots, which is going to be alpha, beta, gamma. So if we were to write that down, it's just going to be minus d over a. So it's going to be minus 26, just 26. Now we've done sort of half the work that we need to do to find the coefficients of this. Now, another thing that you need to do is consider the coefficients of this. And how we consider coefficients of this is that we have to add the roots of the new function g of x together and kind of work our way through it and see what we can do. So we have this function g of x, right? And its coefficient minus b over a will equal 13 over alpha plus 13 over beta plus 13 over gamma. And it's another another coefficient will equal alpha beta plus beta gamma, or rather, sorry, we're going to have 13 over alpha, 13 over beta, and then 13 over beta, 13 over gamma, plus 13 over alpha, 13 over gamma. Now, it may seem a little confusing as to what I've done here, but what I've kind of considered is that let's say I have this function, okay, and I've got these roots for it, a, b, and c. Forget 13 over alpha, 13 over beta, and 13 over gamma now, okay? And if I have these three roots, okay, I have to find every single possible combination of these roots multiplied and added together, okay? So I've just considered that and applied it to 13 over alpha, 13 over beta, 13 over gamma. No matter what the defined root is for a function, okay, a polynomial, the kind of procedure that you follow to get to minus b over a, c over a, d over a will always be the same. It's just the sum of the pairs of the roots, the sum of the triplets of the roots, the quadruplets of the roots, and so on. And then minus d over a is a simple sort of case. It will just be 13 over alpha times 13 over beta times 13 over gamma. Now the easiest, or rather the most plausible thing to do right now is just multiply everything together and see what we can do with it. Now minus d over a is the easiest to work with, because all you have to do is just multiply straight onwards. These are just fractions multiplied together. We're going to have 13 cubed over alpha, beta, gamma. Now the interesting bit over here is that we know the value of 13 cubed, okay, clearly. We're going to have alpha, beta, gamma over here, which we already know the value of because of our original function. Now alpha, beta, gamma is going to be minus d over a, which is just going to be 26 of the original function f of x. That means that we can work out what minus d over a is in the function g of x. So in the end, you're going to have 13 times 13 times 13. I've only expanded it out because it's a little bit easier to work with, and we're going to have 26, which is going to be 13 times 2. Now, if you cross these 13s out, what you get is 13 squared, which is 169 over 2. We've already worked out the value of minus d over a now. So minus d over a, I'll write it up here, minus d over a equals 169 over 2. Very simple. So we can go. Now we're going to try and work with c over a, and it seems a little bit more difficult, and it is, because you kind of have to be fluent with your algebra to see what you need to do, and it also employs quite a bit of tricks, I would say. So c over a equals, if we multiply these fractions out first to try and get 3 whole fractions, we're going to get 13 squared over alpha beta plus 13 squared over beta gamma plus 13 squared over alpha gamma. Now, obviously you can't add these fractions together. There's no common denominator. Okay, it's just alpha beta, beta gamma, and alpha gamma. But what we can kind of consider is that how are we going to make these fractions so that they add up together, i.e. they have the same denominator and they stay the same as before. So the ratio between the numerator and the denominator is going to be the same. Now, but the expression that we know to have all of the common factors of these sort of denominators is alpha, beta, and gamma, because alpha, beta is just missing gamma, beta, gamma is just missing alpha, alpha, gamma is missing beta. So a kind of trick in the algebra that you can use is you can just multiply the top and the bottom by the same thing that the fraction is missing. You can say 13 squared times by gamma over alpha, beta, gamma plus 13 squared times alpha over alpha, beta, gamma plus 13 squared beta times alpha, beta, gamma. Now, just checking if this is the same expression as before, you can just cancel the extra multiplications I've just done and result in this again. So we've kind of confirmed that this and this expression is the same. We haven't changed anything really. But what we do have now is the same denominator, so we can just add this straight on. So it's just 13 squared. I'm gonna preemptively factor the 13 squared out, and I'm just gonna leave inside the bracket alpha plus beta plus gamma over alpha beta gamma. Again, we see that we have these expressions, okay, inside this fraction from which we can substitute our original Vieta's theorems in. So we already know what the value of alpha plus beta plus gamma is. It's 8. We substitute 8 in. Alpha beta gamma is just 26. We substitute 26 in. Kind of repeat this sort of procedure. You get 13 squared and then multiply that by 8 over 26. Again, just splitting up into common factors, we get sort of this final answer, and then 4 times 13 is 52. So in the end, C over A equals 52. The final one, minus B over A, will kind of use the trick in the algebra, but there is a more meticulous method that you can use. It's going to be cross multiplying, and I'm going to kind of show you that method. It kind of highlights how there's a lot of methods in further maths and even normal A-level maths that you can use, so that you can kind of employ the largest set of skills and get the highest possible mark, essentially. Kind of refine your skills in maths and get very precise or get a very precise methodology. Now, finally, we're going to have minus B over A, which will equal 13 over alpha plus 13 over beta plus 13 over gamma right here. Now, if we were to consider what we can do with these sort of fractions, okay, and this is applicable to any fraction, we can just cross multiply, so like this. So we're going to multiply 13 by beta, so we're going to have 13 beta, and then alpha by 13, so 13 alpha over alpha beta, and we're going to repeat that for gamma. Obviously you can use the same method as before, and I actually prefer that method because it's a little bit faster, it saves you time, also it's very reliable. This you can make some mistakes on, but just to kind of emphasize that you can use any sort of method that you want, whatever you're comfortable with. Now we're going to repeat the same thing, like this, okay? And remember to multiply this by the whole of this by the whole of this, okay? So it's going to be 13 alpha beta plus 13 alpha gamma, okay? Or rather beta gamma here. And then it's going to be a 13 alpha beta multiplied like this. And then this is all going to be over alpha beta gamma. Immediately you can kind of see what you can do with this. You can say 13 can be factorized out. You get alpha beta plus beta gamma plus alpha gamma in the brackets, and you get alpha beta gamma as the denominator. Again, substitute. We're going to have 13 times 25 over 26, which will just be 25 over 2. So in the end, what we get is minus d over a, which will equal 169 over 2. So d over a is minus 169 over 2. C over a is just 52. And then b over a, because I'm going to move the minus sign to the other end, it's going to be minus 25 over 2, because you have to consider the minus signs with d over a and b over a as it swaps. Now, we have all the information that we need to answer the question, okay? We have this sort of weird function g of x where we have x cubed plus b over ax squared plus c over ax plus d over a equals 0. And we're just going to substitute all of this into this and get the final answer. We're going to have x cubed minus 25 over 2x squared plus 52x minus 169 over 2 equals 0. Now, it's completely fine for you to leave your answer like this, but if you want to refine your answer a little bit more, such as multiplying everything by 2 to get rid of the fractions, then you're more than welcome to do so. Especially because we defined the original function g of x to be ax cubed plus bx squared plus cx plus d. I think it's better if you multiply the 2 from the denominator out, so you get 2x cubed minus 25x squared plus 104x minus 169, which equals 0. And that will be the final transformed polynomial for f of x if it had roots 13 over alpha, 13 over beta, 13 over gamma of the original roots. If you do have an A-level calculator, then you can check what the answers to this function are when it equals 0, and the solutions for this function, okay, and kind of see that if you were to divide 13 by the reciprocal, or no, sorry, multiply 13 by the reciprocal of alpha and beta and gamma, you'll see that the answer should match up. So this is the final answer. And this is one of the many questions that you can get asked on your WJC paper. This one particularly was worth 6 marks. So all the marking points over here have been covered. This is just extra stuff over here, for example, like defining f of x and g of x to kind of refine your answer even further and secure those marks.